This lesson introduces you to a simple class that will read a graphics file from disk and store it in memory. The memory resident form of a graphic image is held inside an object of the image class. The image loader class extends the component class. The reason it needs to extend the component class is because it implements an interface named image observer, which requires the presence of a method that tracks the loading of an image into memory, and that method exists in the component class. Now, this class has no main method and no constructor. It's a utility class with one public method, load image from file. This method is given the name of a graphics file and returns an image object containing the graphic information from that file. The toolkit class has a static method named getDefaultToolkit that returns the address of the default toolkit object. The toolkit class is the basis of the abstract windowing toolkit and contains many of the low-level operations, and you usually don't have to use it. One of the low-level operations that does come in handy is the getImage method that loads a graphics file into an image object. Well, it doesn't exactly load the image. It schedules the loading of the image and then returns to its caller. When getImage returns, the file is not yet loaded. This means that the program could go on about its business and check back later to see if the file is loaded. But in this example, we just want to wait for the image to load. This method is here just to wait for the image. A media tracker object is created to do the waiting for us. Notice the argument to the media tracker constructor. This is a Java keyword, and it's the way an object refers to itself. You know, when you want to refer to an object, you use the name of the reference holding its address. Well, the keyword this is the name of an object's own reference. The constructor of media tracker requires a component object be passed to it, and this is a component object. In fact, that's the only reason this class extends the component class. If this code were inside a canvas or a frame class, it would work just as well because they're also components. Now, the media tracker can be given a collection of images, one image at a time, and it will track their status. The way to add an image to the list of those being tracked is to call addImage as we do here. Notice the second argument. That's an ID number. If you're going to be loading lots and lots of images, you can assign ID numbers to them and wait for them all to come up according to the ID numbers. The ID numbers will put them in groups. In this example, we're not going to do that. We're just going to add one image to the list and wait for it to load. A call to the method waitForAll will not return until all images are completely loaded. So we call the method, and when it returns, the image has been completely loaded and is ready to be displayed. But I'm sure you noticed this little thing here. The try and catch statements are part of the Java error handling system, and I'll be going into more detail on that later, but for right now, let me just give you a quick overview of what's happening here. The waitForAll method could encounter an error while trying to load an image. It could be that the file is corrupt, or it doesn't exist, or whatever. But whenever you are dealing with input or output, things are going to go wrong. If such an error does occur, then the waitForAll method will throw an exception. What this means is that waitForAll will construct an exception object explaining the situation, then it will throw the exception object to its caller. When it throws this exception, it abandons all processing at that point and returns to this method. That's where the catch comes in. If an exception of the type specified in the catch statement is thrown, then the code inside the catch block will be executed. In this example, a method of the exception object is called to print out some information about what has taken place, and then system exit is called to end the program. However, if everything goes right and the image loads, this method will return with a fully loaded image, and that image is then returned to the original caller. In the next lesson, we'll use this image loader class to load an image, and then we'll display it in a Canvas window. The program described in this lesson uses the image loader class created in the previous lesson to load a graphics file and display it in a window. Once the image is loaded, the method for displaying it is quite straightforward. All you need is your graphics object. The display class extends the frame class and is much the same as previous programs that extended the frame class. One difference here is that in the main method, the name of the file to be displayed is read from the command line. First, the count of the number of arguments on the command line is tested to make sure that it's exactly 1. This program only knows how to deal with one thing on the command line, and that one thing must be the name of a file. Now, the file could actually be a JPEG, GIF, or a PNG. Any one of those three can be loaded and displayed. By the way, Java doesn't pay any attention to the suffix on the file name. Java looks at the content of the file itself to determine the type. So you can name it anything you like, but it must be one of the three, a JPEG, a GIF, or a PNG. A new display object is created here, and the file name from the command line is passed to the constructor. This is the constructor that accepts the file name, and this is the line that creates a new display canvas object using the file name passed to the constructor. This is the display canvas class. It is a display canvas that loads an image from disk and displays it. It only has one constructor, and that constructor requires the name of the file. A new image loader object is constructed, and the method is called to read the file and convert its contents into a memory resident object. The height and width of the loaded image file is retrieved, and the window is set to the correct size to display it. At this point, to make the program a bit more robust, you'll probably want to check to see whether either the width or the height is 0. This happens if the file was either empty or did not exist. As this program is now written, it will display a 0-sized window, and that's okay with me, but an image object is always returned from the loader even if there was no image on disk under the name specified. The paint method calls the method drawImage of the graphics object to paint the image into the window. It's sort of like drawing a rectangular shape on the window. You specify the image object and then the XY coordinates of the upper left-hand corner to position it in the window. In this example, we made the window the same size as the image, so displaying it in the far upper left-hand corner will just fill the window. The this argument passes a reference to the current object, which is the display canvas object. What is needed here is an image observer object, and every component is also an image observer object. This all has to do with a situation where an image being displayed is not yet finished loading, but we aren't dealing with that here, so we can ignore that situation. In fact, if you aren't going to be using the information, you could just as well pass null instead of this. The keyword null is a special reference that has no value. That is, it's not the address of anything and is recognized as such inside this method, so if you pass null instead of this, it's just ignored and everything proceeds normally. Let's compile this and see if it works. Along with the example programs, I have provided a public domain JPEG file. You can find lots of these on the NASA website. There's Mars, as seen by the Hubble telescope on the day that Mars was closest to Earth. I have converted one of the NASA files to a PNG file, and it can be displayed by the same command. Whenever I see this picture, I want to grab a hold so I don't fall off. In the next lesson, I'm going to show you how to write a program that will load and display an image from somewhere on the internet. In this lesson, we're going to modify the programs from the previous lesson and load an image file from a server on the Internet. The first thing to do is modify the image loader class so it can reach out over the Internet and load a graphics file from a server into local memory in the form of an image object. Well, Java has just the thing to do that. All that's necessary is to add a new method to the class. This means that this class can now be used not only to load images from the local disk, but also from the Internet. This new method is named loadImageFromInternet, and it requires a URL string, just like the one you type at the top of your web browser. The URL must be the full path and include the name of the graphics file somewhere on the Internet. A new URL object is created based on the character string passed to the method. The new command is inside the try block because the URL string could be badly formed, and if so, the constructor of the URL class will throw an exception. If the URL string is badly formed, the program dumps the information and exits. Now, the URL may not be correct. That is, the location may not actually exist on the Internet, but that won't cause any problems here. The only error that comes about here is if the string is not in the correct format of a URL. Just as was done when we were reading from the disk, we get an address of the default toolkit and call the getImage method. But notice the argument being passed to getImage. This time it is a URL object instead of a string of characters. The getImage method is overloaded in the URL class. That is, there are two versions of the method defined in the class. One of them takes the name of the file and the other one takes a URL object. Just like when we were loading the image from a file, we have to call the waitForImage method to pause long enough for the image to fully load into memory. In this case, with the image coming from the Internet, the wait is more important and it will certainly take longer. It could take significantly longer depending on the speed of the Internet connection. At any rate, once the image is loaded, the method returns to its call. Now it's a matter of writing a program to load a remote image and display it. It's fundamentally the same as the program that loads and displays a graphics file from a local disk. I simplified things a bit in this version by hard-coding the URL string to the name of a graphics file that I happen to know exists on the Internet. This constructor creates an image loader object and calls the loadImageFromInternet method to load a graphics file from the Internet. The rest of the code is the same as in the previous example. The height and width of the loaded image are used to size the window. Then the paint method calls drawImage to display the image in the canvas window. Compiling and running the program looks like this. And there's the old man in the craters and all. In the next lesson, we're going to look into modifying a loaded image by changing its size. This lesson demonstrates a technique for changing the size of an image. Two images are loaded and then reduced in size and displayed in the same window. This is the Display Scale Canvas class that loads two of the images we've used in previous lessons and reduces both of them to the same size for display. The window is set to a rectangle 256 pixels wide, 128 pixels tall. This program will resize two images to fit side by side inside this rectangle. An image loader object is used to load the blue marble image from a file. The getScaleImage method of the image object is called to produce a new image No matter what its original size, this method call will produce a version of it that's 128 by 128. Scaling requires that pixels be added, removed, or in some cases, both. There are different ways of doing this, and you can specify the way you would like to have it done. This selection specifies that the new pixels be set to an average of the pixels around it. You can also specify scale smooth, which tends to produce a smoother image. Or you can specify scale replicate, which means that the new pixels will be an exact copy of one of the pixels adjacent to it. If you need speed, you can specify scale fast, and the fastest algorithm will be used. Or you can specify scale default, and the default algorithm, whichever one that happens to be, will be used. The default will vary from one platform to the next. Now this is a call to the same wait for image method that we used in the previous examples to wait for images to load from disk and from the internet. In this case, the method will wait for the image to be converted to its new size. This method will wait for a new image to be completely loaded no matter what its source. In this case, the source is another image in memory, with its pixel values being passed through a process to create a new image. With images as small as these, the transformation is very quick, but with a large image, it could take quite a bit of time. This same sequence of method calls is made to load the red marble image and use it to produce a scaled-down version. Once the constructor has completed execution, these two image objects should be ready to be viewed. They should each be squares of 128 pixels on a side. The two reduced images are drawn side by side in the window. The little red image is drawn on the left, and the little blue is drawn 128 pixels to its right, which should put the two images side by side and just fill the window. The class did not compile because, as you can see from these two error messages, the wait for image method is private and cannot be accessed from here. The logical thing to do is to make it accessible. Now it's a public method. We need to compile the class, so the class file will have this new information. Now we should be able to compile the display scale class without any errors. And that should make it possible to display the two images at once. Here are the red and the blue marbles side by side. Any image can be scaled to any size, but be careful when you are expanding them because you can wind up with indistinct pictures and jagged edges. When you shrink them like this, you almost always wind up with a picture of a quality equal to the original, but expanding the shrunken ones again can cause some deterioration because some data is inevitably lost when you do shrink it. In previous lessons, we've drawn and painted all sorts of things on the screen. Some of the pictures were built up by drawing one thing after another directly onto the screen every time we wanted to update the display. There is another approach, and there are places where drawing composite pictures in memory really comes in handy. For one thing, if the picture is complex and takes time and resources to render, you only have to do it once and then you can put it on display whenever you like. This is the Draw Memory Canvas class. It's a canvas that creates an empty memory resident image object, then paints some things into it. The image object is then painted to the window of the canvas so we can see what it looks like. We're going to be loading an image from a file, so we'll need an image loader object. Of course, we could just copy the code from the image loader class and put it in this class, but you can see how convenient it is to have stuff that you can use over and over again. The call to load image from file loads the graphics file and stores its image here as an image object. Using the height and width of the loaded image, the height and width of the window is set. That's all that's done in the constructor. The rest of the action is in the paint method. At the top of the paint method, there is a check to determine whether the reference named image is null. If this image reference has not been initialized by the paint method, it will be null because Java always initializes all variables and all references are automatically initialized to null. The call to the createImage method creates an empty memory-resident image object. The createImage method is part of the component class, and the canvas class extends the component class, so it inherits this method. Once the window has been realized, and we know it has been realized now because it has come time to paint stuff on it, you can create all the image objects you need. In later lessons, we'll be looking into why you might want to create image objects over and over again. Now, just like a window being displayed, every image object in memory can produce a graphics object that you can use to draw to it. This means that every method used to draw into a window is also available to draw into an image in memory. Well, there is a special limitation. This is true only of empty image objects that you create the way this one was created. The image object that was created by loading the file won't let you have a graphics object, but that's okay. All we need is the empty one to do everything we need to do. Using this new graphics object that we got from the memory resident image object, we call the drawImage method to draw the loaded graphics image file into it. They're exactly the same size because that's the way we created the image. But we don't stop with that. Here we create a new font and set it into the graphics object of the image and draw a string of characters on top of the blue marble image that we've already painted there. Now all of this will only happen once. Once this block of code has executed, the reference will continue to hold the address of our memory resident picture, so this entire block of code will be skipped from now on whenever paint is called. The actual rendering to the window is made with a call to drawImage to place a copy of our memory resident image on display. After the first time through, if the paint method is ever called again, this is the only code that is executed inside the method. Several things can cause the paint method to be called again. If the window becomes obscured and then is made to reappear, the paint method is called to make it display itself. If the window is minimized and then pops back up, the paint method is called again. Whenever the size of the window is changed to either larger or to smaller, the paint method is called again, and it may or may not adjust itself to this new size. This program does not have any size adjustments, but we'll be doing that very thing in a future lesson. Remember the checkerboard program you wrote in the last chapter? Well, your assignment now is to write another checkerboard program, but with some differences. For one thing, all dark squares are to be made from an image that you've loaded from disk and rescaled to fit the size of the square. The overall size of the checkerboard is to be 8 by 8. That is, you need to display the same picture over and over again for a total of 32 times. So half the squares in the checkerboard show the image. You can use any image file you like because the method that scales the size of the image will expand it and contract it to fit whatever size you specify. The program you write will have the name of an image file built into it, but if you specify the name of an image file on the command line, it will be used instead of the one that is built into the program as the default. A title of some sort, the name of the program, the name of the image file, or both, appears on the bar at the top of the frame of the window. The method of the frame class that does this is called setTitle. The default is for no title to appear, but any string you specify in the argument to this method will appear on the bar at the top of the window. The frame class also has a method that you can call to prevent the user from resizing the window. Calling the method setResizable with the argument of false will fix the window's size and not allow it to be altered. The default is to allow the user to resize the window. Well, that's it. You should have everything you need to write this program. The only things that are new are the ones listed on the screen right now. To make myself perfectly clear about what I mean for this assignment, let me show you the output of the program that I wrote to do this very thing. And there it is. I used the blue marble PNG for each of the images, scaled to 64 by 64. The overall size of the window is 512 by 512, and that gives me an 8 by 8 grid of 64 blocks. Notice at the top of the window, in the bar, there is a title that includes the name of the program and the name of the image file being used. Now, this program will accept another image file on the command line like this. And there we have the same program, but with a different image file. In the next lesson, I'm going to show you the source code of this program and exactly how this was achieved. This lesson is a detailed description of the program solving the problem in the previous lesson, and then a modified version of the program is presented with an added feature. This is the program that displays the checkerboard with a graphics file loaded from disk and displayed in all the dark squares. The first thing handled by the main method is the argument on the command line. If there is exactly one argument on the command line, it's taken to be the name of the graphics file, and the name is stored for later use. If there is anything other than one name on the command line, the default graphics file name is used. Once this has been decided, a picture checkerboard object is created. The first method called by the constructor is setTitle to specify the string to be displayed at the top of the window. In this case, the string is a combination of the name of the program and the name of the image file that's being used in the checkerboard. Recall that a plus sign between a couple of strings combines them into a single new string object. A call is then made to setResizable with the argument false. This means that whatever the size of the window when it first appears, it will remain that size until it's closed. The name of the selected file is then passed to the constructor of the PicCheckCanvas class. The constructor of the PicCheckCanvas class uses the file name passed to it to load an image file. The window is set to the correct size, and the image is loaded from the file. The getScaledImage method is called to create the scaled picture image, which is the size we need for the squares in the checkerboard. In the paint method, there is one for loop nested inside another. This is the same sort of loop mechanism used in the previous example with the 4x4 checkerboard. All that's changed is the number of times through the loop, and the fact that an image is used to draw the square instead of simply a rectangle. And that's all there is to it. As I showed you earlier, the program can be run to create a checkerboard made up from any image file. Let me show you another version of the program with something added to it. On most operating systems, when a window is minimized, it shows an icon. The frame class has a method you can use to specify the icon. Now this program is just like the one I've already shown you, except it also defines an icon image. To keep it simple, it calls the setIconImage method with the same image that's being used to construct the checkerboard. You don't have to select an image of the correct size. It'll be scaled to whatever size is needed. Of course, this only works on systems that actually use icons to represent programs. Because the setIconImage method is a member of the frame class and it requires an image object to be passed to it, it was necessary to load the image here in the constructor of the frame so the method could be called. To prevent the necessity of loading the image again, the one that has already been loaded is passed to the constructor of the IconCheckCanvas class. The constructor of this class accepts an image object passed to it. And this is the image object used to create the scaled version to fit in the checkerboard squares. As you can see on this version of Windows, an icon shows up in the upper left-hand corner of the frame bar at the top. The same icon